Hello everyone, this is Kinjal Parmar. Today we will discuss binary adders. So let's start. Binary adder. A binary adder is a digital circuit that produces the arithmetic sum of two binary numbers. A binary adder can be classified according to its bit operation as binary serial adder. That means one bit at a time, and we have a bitwise addition serially in binary serial adder. In binary parallel adder, all bit at a time. So we have a output bit or say some bit parallelly. A binary serial adder requires one full adder to perform n bit addition, so it is simple and time consuming. A binary parallel adder requires n full adder to perform n bit addition, so it is quite faster than serial adder. Binary serial adder. Binary serial adder is a combinational logic circuit which is used to add two numbers serially and produce some bits as a serial outputs. Serial addition of n bit number requires only one full adder. Using full adder, we can add 3 bits and we have a 2 output sum and carry. Now, if we have a 4-bit number or 8-bit number or says n-bit number, then how we can add this number as full adder? Only add just 1 bit. So here, if we want to perform n-bit addition serially, then here we have a 1 full adder circuit. Here we give 1 by 1 input AI and DI. That means for if we have a 4-bit input A3, A2, A1, A0 and B3, B2, B1, B0, then start from A0, B0. So first add A0, B0 with this full adder. So we have a sum bit for S0 and we have a carry bit for C0. After addition of A0, B0, give A1, B1 and previous carry C0. So here then next addition of A1 plus B1 plus C0. So we have a S1 bit and C1 carry bit. Then for next give A2, B2 and here we have a carry bit C1. So for third significant bit we have a over here A2, B2 plus C1. So we have a sum bit S2 and carry bit C2. Then for most significant bit A3, B3 and carry C2. So here A3, B3 plus C2. So here we have a S3 bit and if there is a out carry then we have a C3 bit. So this is how one by one all bits entered into this one full adder and we have a this sum and carry bit serially. Binary parallel adder. Binary parallel adder is a combinational logic circuit which is used to add two numbers in a parallel form and produce some bit as a parallel output. Parallel addition of n-bit numbers require a chain of n full adders or a chain of 1/2 adder and n minus 1 full adder. For example, addition of a 4-bit number requires 4 full adder. Here one example for this A0, A1, A2, A3 and for this B0, B1, B2, B3 addition, we can add this number as 1 plus 1 sum 0 carry 1 then 1 plus 1 plus 1 sum 1 carry 1 then 1 plus 0 sum 1 carry 0 and then next 0 plus 1 plus 0. So we have a 1. So here we have a two types of carry, input carry which results from previous addition and we have a output carry. So this is how we perform 4-bit addition. To perform this in a parallel adder circuit, here we have a logical diagram. Using this 4 full adder, we can perform 4-bit addition. This A0, B0, A1, B1, A2, B2, A3, B3 entered parallelly. That means all bit at the same time. Here first A0, B0 added, and if there is a previous carry C0, so we have a a0 plus B0 plus C0, and we have a sum output S0 and carry C1. Then this carry of this bit can be forwarded to the next step, or says next addition. So here we perform A1 plus B1 plus C1. C1 is a previous carry from the previous stage addition. So using this addition, we have a S1 bit and C2 bit. Again, this C2 is a carry resultant from previous stage. So here again add this as a A2 plus B2 plus C2. So we have a S2 bit and we have a sum bit carry bit. Forward this carry to the next stage, and we have a fourth full adder performance as a A3 plus B3 plus C3, and we have a S3 sum bit and C4 carry bit. So this is how binary parallel adder work. Here we entered these bits A and B parallelly, but here carry of previous stage forwarded to the next stage. After the calculation of addition, and we have a sum bit and carry bit. So let's discuss about another adder, binary carry look ahead adder. In a parallel adder, carry output of each full adder is given as a carry input to the next higher order state. Hence, this adder, it is not possible to produce carry and sum output of any state unless a carry input is available for that state. Basically, in a parallel adder, we give all the bits parallelly, A and B, all the bits parallelly, but we have to wait for a carry of previous bit for the addition of next bit. So we have to wait for the carry of a previous stage. So for computation to occur, the circuit has to wait until the carry bit propagate to all states. This induces carry propagation delay in the circuit. For the computation of a large number of bits, more stages have to be added, which make the delay much worse. Hence, to solve this situation, we have a carry look ahead adder. One widely used approach to employ the principle of carry look ahead solve this problem by calculating the carry signals in advance based on the input signal. This type of adder circuit is called as a carry look ahead adder. So here what we can do, we can calculate carry previously from the input signal, so we does not have to wait carry propagations. So how we can do this? The carry input at any stage of the adder is independent of the carry bits generated at the independent stages. Hence, the circuit at any stage does not have to wait for the generation of carry bit from the previous stage, and carry bit can be evaluated at any instant of time. So to understand this, let's define two variables as carry generate Gi and carry propagate Pi. Then we have a Pi is equals to Ai XOR Bi and Gi is equals to Ai into Bi. Basically, this is the equation of sum and carry, right? So here we consider Pi as a Ai XOR Bi and Gi is equals to Ai dot Bi. The sum output and carry output now can be expressed as Si is equals to Pi XOR Ci, because basically we have a sum S is equals to A XOR B XOR C. So here this can be represented as Pi XOR Ci. and this Ci plus 1 is equal to Gi plus Pi into Ci, where Gi is a carry generate which produces the carry when both Ai and Bi are 1 regardless of the input carry. Pi is a carry propagate and it is associated with propagation of carry from Ci to Ci plus 1. Now using this equation, how we can calculate carry already? So the carry output boolean function for each stage in a 4-stage carry look ahead adder can be expressed as we have a C in is equals to input carry, then next carry C1 is equals to G0 plus P0 C in, which is resultant from the previous carry output. Now for C2, we have a equation G1 plus P1 into C1. Now here we have a value of C1 which is G0 plus P0 Cin. So put this value over here and simplified terms. So we have a C2 is equals to G1 plus P1 G0 plus P1 P0 Cin. Then for C3, we have a equation G2 plus P2 into C2, and we have a equation of C2 over here. So we write G2 plus P2 G1 plus P2 P1 G0 plus P2 P1 P0 Cin, and for C4 G3 plus P3 C3, so which is equivalent to G3 plus P3 G2 plus P3 P2 G1 plus P3 P2 P1 G0 plus P3 P2 P1 P0 Cin. This equation resultant of the previous stage. So using the value of previous stage carry, we calculate the equation of next carry. In above Boolean functions, C4 does not have to wait for C3 and C2 to propagate, but actually C4 is propagated at the same time as the C3 and C2 because this C2, C3, C4 depends on G1, G0, Cin. Basically, no previous carry, only dependent on Cin, that is input carry. Since the Boolean expression for each carry output can be implemented with a one level of AND gate followed by an OR gate. So using this equation, we have a binary carry look ahead generator. So using this generator circuit, we can calculate carry previously. So here we have a binary carry look ahead generator circuit which result from the equation of C3, C2, C1. So this is how we can calculate carry independently. Now using this carry, we generate binary carry look ahead adder. So here we have a carry look ahead adder and we have a equation for sum bit and carry bit. Sum is equals to P XOR Ci. So this is how we can implement sum bit S3, S2, S1, S0. S is equals to P XOR C. So this is how we calculate carry independently and we save here time and we can calculate carry independently using this carry look ahead adder, and we have a sum bit and carry bit parallelly, and this carry look ahead adder is a faster than binary parallel adder. Now let's discuss about BCD adder. A BCD adder that adds two BCD digits and produce a sum digits in BCD form. The two decimal digits together with the input carry are first added in the top 4-bit adder to produce the binary sum. When the output carry is equal to 0, nothing is added to the binary sum. When it is equal to 1, that means invalid BCD value, hence binary 0, 1, 1, 0. That means 6 is added to the binary sum through the bottom 4-bit adder. So this is how we can perform BCD addition. A BCD adder that adds two BCD digits and produce a sum digit in a BCD. The two decimal digits together with the input carry are first added in the top 4-bit adder to produce the binary sum. This binary sum may or may not be in BCD form. So we have to convert this into correct BCD form, and for identification of correction we have a one condition. The condition for a correction and an output carry can be expressed by the Boolean function C is equals to K plus Z8, Z4 plus Z8, Z2. When the output carry is equal to 0, nothing is added to the binary sum. And when it is equal to 1, that means invalid BCD value, hence binary 0, 1, 1, 0. That means 6 is added to the binary sum through the bottom 4-bit adder. So this is how we can calculate BCD addition, and we have an answer in BCD form. Now let's discuss this BCD addition procedure with one example. Perform BCD addition 5 plus 6. So we have a 5 in BCD format like 0, 1, 0, 1 and 6 as a 0, 1, 1, 0. Here we perform binary addition. So 1 plus 0, 1, 0 plus 1, 1, 1 plus 1, 0, carry 1, and we have a 1 plus 0 plus 0, 1. So here we have a value 1, 0, 1, 1. This number 1, 0, 1, 1 which is greater than 9. So BCD number which is greater than 9 is a invalid BCD number, and for correct BCD format we have to add 6. 6 that means 0, 1, 1, 0. Why 6? Because for a 4-bit binary pattern, we maximum can be represent number 15, and but in a BCD we can represent up to 9 only. So this difference 15 and 9, total difference of 6. So to correct this invalid BCD number, we have to add this 6, 0, 1, 1, 0. After this addition, we have a correct form of BCD number. So here 1 plus 0, 1, 1 plus 1, 0, carry 1, 1 plus 1, 0, carry 1, 1 plus 1, 0, carry 1. So we have a 1. So here we have a first 4 digit as a 1 and another 4 digit as a 1. So basically it is a decimal equivalent of 11, and this 11 can be represented in a BCD form like this. So using this method we can add a number in BCD format, and we have an answer into BCD format. Now how this can be done using a circuit? So we have a BCD adder over here. Here we use 4-bit binary adder. Here we use two 4-bit binary adder. This first 4-bit binary adder used for binary sum, and then another 4-bit binary adder used for correction of a binary sum into correct BCD format. Now here we have a 4-bit number A and B. This A and B added over here into 4-bit binary adder, and we have a value, or says we have a sum bit Z8, Z4, Z2, Z1. This 8421 represent weight, and also we have a output carry K. So here we consider this K as a output carry. Now we have a invalid BCD number for addition of 4-bit if this K output occurred. So here this given as a correction equation for next binary adder circuit for correction. Then we have a BCD adder equation. C is equals to K plus Z8 Z4. Now why Z8 Z4? The BCD number which are greater than 9 is an invalid number. So for invalid number, we have a two condition, like if there is 8 and 4, both are 1. So 8 plus 4, 12. That means the number which have a weight of 8 and 4, these are invalid number, as well as this 8 and 2. If we have a number which has a this both weight at a time, so this number is also greater than 9. So again this number is invalid for BCD, and we have to correct this. So for the condition of output carry, and for this Z8 and Z4, and for Z8 and Z2, we have to correct this binary sum into correct BCD sum. So here we draw a logic diagram for this correction. K plus Z8 into Z4 by this AND operation, and Z8 into Z2 by again another AND operation. So here we have a output carry says C, and this C is connected for the next addition. Here we in next 4-bit binary adder, we add Z8, Z4, Z2, Z1 plus 0 C C 0. Here if we have a this carry as a C, so here we have a bit 0 C C 0 plus this binary sum bit. If we have a bit which are greater than from 9, for example, if we have a answer 12, so that means these are 1, so we have a 1 over here, and after OR operation we have a 1. So ultimately this become as a 0 1 1 0. So our aim is to add 6 into this binary sum whenever we have a invalid code. And for invalid code, if we add 6 over here, then we have a correct BCD sum over here. So this is how we correct this binary sum into BCD format. If we have a valid code, then we have a 0 over here, 0 over here, and 0 over here. So we have a ultimately 0, 0, 0, 0 over here. That means nothing will be added into this binary sum, as this binary sum is in a correct BCD format. So this is how this BCD adder works. So in this session we discussed about various binary adder like serial adder, parallel adder, carry look ahead adder, and BCD adder. Thank you.